instead of using the fours.
I'll take.
So
So Ignatius, do you want to turn the cameras on here, everybody?
yeah,
and then
let me
take
give
a picture?
everyone permission to turn on their cameras so that
Okay.
we can do this. I'll turn mine on. So everybody turn on you may turn on your cameras, please, so we can do that screenshot.
No.
We still.
I know I gotta.
Well, let me do the view change the gallery, right? I think some of you, Anderson, Mandel, Dwayne, could you please turn on your cameras so we can get that screenshot? I'm not good at doing this, so if some of you know how to do it, you can take the screenshot and send it to me as well as a
I'm gonna
backup.
try my
Dwayne,
best here.
are you on, Dwayne? We're missing someone. Let's see. I don't know if Dwayne is understanding how to do that.
Well, it's good to see everybody.
Yeah, it is.
You have to look at me, so I guess I can look at you guys too.
Okay. So let's say water. Yeah, that's a better one, Shannon. Well, you know, all these years we doing this thing and I don't know who is Shannon, right? You had some better light on, Shannon. You went off a bit. Yeah, that's better. Good. All right. Okay, thank you. I think it's saved to my OneDrive. So good to go.
Perfect. Thank you. Okay, give me 2 seconds. I took a picture of the PLC cabinet here. I'm just going to bring the picture up, so just bear with me here. I think it's a good picture to see, so we'll bring that up. There was a comment that the PLC thing looked pretty confusing. Oh, just you wait till you see this one. I feel really bad for people who have to do this for a living because wow, there's a lot there. So just bear with me and I will bring that picture up. All right. I just got to find where it stores it. That's all. Give me a second, you guys. Sorry about that. I just think it's worth seeing if I can get that picture up. I think here we go. Two, three. All right. Okay, I'm going to share the screen again. Pictures up here. Find you guys again. I'll share my screen. Okay, so you should see a picture of a panel. Give me a thumbs up if you can see that panel. Should be just, yeah, good. Okay, so that's our PLC panel. It doesn't look like much, but just wait till I give you the next picture because it does get ridiculous really quick. So when I open up that particular panel, there we go here, and you can see here, and you thought that it was pretty confusing before. This is one that I just took now for our plant here. And you can see, look at the wiring and stuff. It's pretty ridiculous, really. And just to give you an idea for size, I'll do this next photo. So come up here. There we go. What happened there? Try that again. I know it's really blurry, but that's to give you the idea of height. Like I'm close to 6 feet tall, and this is a huge panel. So that's a typical PLC panel for our plant here. So imagine how important, yeah, you're right, Shannon, for labeling. And labeling is key, because if it's not labeled correctly, imagine the nightmare that this would be. It's becomes a problem very quickly. Okay, let me just set the presentation back up here, and then we will keep going. All right, can you guys see that control system again here? Keep going. Back up here, there we go, perfect. So that's a typical PLC panel, and that's huge, right? It is definitely, you know, it's not a typical operator can get in there and mess around with that. So let's talk about some drives, and we're going to talk about both electrical drives and mechanical drives, because both are really, really important. When we talked about electrical drives, there's a bunch of different styles here. First one's a fixed speed. And basically that's, you turn a pump on and it does what it needs to do, right? If it's 10 horsepower pump, when you turn it on, it will provide 10 horsepower worth of work. And it does it as soon as you turn it on. And sometimes that can be really hard on a piece of equipment. Second one's called a soft start. If you have a soft start, what happens is it uses less energy. So when you first start it, it comes on slow, and over time it gets to full speed. So you don't use a lot of amperage and a lot of power to get this thing moving. It will start up very, very slow and ramp itself up. Bigger motors typically use a soft start, and think of it as it kind of works its way to full speed. It doesn't just turn on and it's full speed, else that would just cause too much damage or too much power draw. So they use something called a soft start, and it will help, you know. And again, we talked about water hammer and stuff, right? If we turn a pump on too quickly, it could cause a lot of water hammer. So if we use a soft start, it will actually ramp up very slowly. But once it's ramped up, it's a fixed speed. It does not vary after that. It is 100% fixed speed. Some of the new stuff we see out there is variable speed drives, and they also call that a VFD, or a variable frequency drive. And that will actually move around, right? It will go up and down the best we can. It's used to vary the operating speed of equipment. So if I want to maintain a tank level, it will actually speed up. So as the tank starts to drop, the pump speeds up to fill the tank. As the tank fills up, the pump will slow down. So it's always varying the amount of output to match whatever you need. In this case, it would be level. So those are variable frequency drives. One of the big projects I'm working on right now is I'm taking my pumps, those big 400 horsepower pumps, and they were at one time soft start. So when I turn them on, it would slowly over time get to the full speed, but then that's all I have. I'm converting them to variable frequency drive, which means that I can set a set point and I can vary the difference. And that's really important. So pumps, what are the main purposes of pumps? And again, from a definition standpoint, is to add energy or add pressure to a water system. And again, because levels equal the pressure, it also will provide more lift. It will lift water from a low elevation to a higher elevation. It keeps pressure in your distribution system, which is super important because we want positive pressure. It will meet the customer flow requirements or the customer pressure requirements. Typical minimum pressure is about 20 PSI. And, you know, I'd say anything between 30 and 70 is pretty typical for domestic pressure. Once you start getting over 100 PSI though, you can start getting internal damage into some of the piping and fixtures in your house. And that's something that you should look at having a pressure reducing valve at that point in time. When we talk about pumps itself, some of the definitions is low lift and high lift pumps. And I've seen these used a bit sometimes in the exam purposes. So low lift pump basically takes water from your supply to your treatment plant. And that's always called a low lift. Where if we're taking it from our treatment plant into the distribution, it's called a high lift pump. And that's
I think you froze for a bit.
Low lift pump, and if it's high lift pump, am I okay now?
Yeah.
Okay. Sorry about that, you guys. So low lift and high lift pumps, super important. There's all the different types of pumps out there, right? Well pumps, booster pumps, standby pumps, and sometimes fire pumps are all used for different purposes depending on what's needed. A well pump again that's a supply, and it's a form of a low lift pump, and it takes water from your supply or your well in this case, and takes it to the plant. Any booster pumps usually are after the clear well, and it boosts it to a reservoir or to a neighborhood. Standby pumps can be used, say, if pressure in the system is starting to get low, these will come on to boost the pressure in the system. And sometimes if you open up a fire hydrant, that becomes a real problem. It will reduce pressure in the system, and pumps sometimes have to come on to compensate for the amount of flow and pressure loss by opening a hydrant. So there's fire pumps. I have all of these in my system right now. Again, for best performance and efficiency, pumps should always be operated within the design range, and it looks at flow and amount of head, and that's in the lift. And you're always going to look at your manufacturer to make sure that that is done properly. And we'll take a look at some of the curves and some of the things that have to happen to allow that to work better. We talked a little bit about centrifugal pumps. And again, remember we talked about how the lower center of gravity pulls water in. The impeller will spin, pushing that water from the center out to the outerwards and causing that lower vacuum, right? And causing the water to get sucked in to the impeller. And basically the discharge pressure depends on how big that impeller is, how fast that impeller is moving, you know, the amount of power and flow, right? These are basically the things that dictate the discharge pressure. You always have a check valve, and we saw that last lesson that the check valve is always after the pump, and that tries to keep the water inside that pump bowl so that when you start to pump, it will pump water, because that pump bowl has to be in water in order for it to produce that vacuum. The other one we talked about last lesson was the positive displacement pump, right? And that delivers a constant volume with each stroke or pulse, and flow is controlled by a stroke length or some sort of speed or variability of the stroke. Again, one thing to talk about with, you know, and again shows up at the in the test, that Centrifugal pumps, you can have the discharge valve closed. It's not going to harm the pump. The positive displacement pump, however, if the valve is closed, it will build pressure. And it builds pressure to the point where you'll damage the piping or damage the pump itself. So never ever start that pump with the discharge valve closed. And I've seen this question come up on the ABC exams a fair bit. Vertical turbine pumps, again, a vertical turbine is a centrifugal type pump. This is the one that's under the floor, right? And it has the different stages. And you can see here, this particular one has a number of stages. More stages, the more lift, the more you can lift the water. So always remember that more pressure or more lift equals more stages. Sometimes we see some submersible pumps, and these are pumps that you can't see. They're submerged in the water. Typically, you see these more in the wastewater industry, but sometimes you see these used in water reservoirs and stuff. The pump will actually be submerged in the water itself. The water actually helps cool it as well, so keep that in mind. It actually designed to work well while it's underwater. And I'll just get my pen for this one. One of the things I see here, they call it a water seal. And a lot of the older pumps, in order to seal the shaft from leaking, so normally, right, if water could come through here and actually leak out. So what they're gonna do is they seal it with a packing. These little squirrels here are packing. And they're usually like a graphite type packing material, and it works well, but it needs to be a little bit wet. So it has to be a bit of a drip on there. So usually you have a water supply that's coming in, and water here with the graphite packing is used to lubricate the shaft against it. It does two things. It lubricates and seals up the shaft to the pump housing, and it prevents water from inside the pump from getting outside the pump. One thing with this is that you got to always make sure that packing is good, because it does wear over time, and that the water supply is there. One of the things that new operators tend to do, they go, uh-oh, it's leaking, and they turn the water supply off, and they're therefore causing damage to the shaft due to heat. The water seal provides a seal and also provides lubrication and cooling, and that's important to have. So there always should be water leaking out of that style of packing. It's messy. Some of the new stuff we see is mechanical seals, and they don't require the same amount of water or any at all. So there's different types out there. So somebody who's come from mechanical seals all of a sudden sees a packing system and there's water pouring out of it, it's okay. So always understand what type of packing or mechanical seal that you do have, because that's a really common mistake with new operators. They shut off the leaky packing and all of a sudden it becomes an issue. So again, back to troubleshooting and operating, right? So before you pump, you gotta check that pump out pretty good. You're gonna rotate the shaft to see if you can, in some of the smaller pumps, rotate it to see if you hear any bearing noise, to see if it turns freely. You're gonna test the electrical circuit, and that's usually done by electrician. You lubricate the bearing. One of the things is don't over lubricate. If you over lubricate a bearing, it will actually cause heat issues. So it's important not to over lubricate any of the bearings. And that actually, I've seen that question come up in a number of the ABC tests. So make sure that you are not over lubricating. When you do start the pump, and what I like to do when I install a pump is actually draw a little arrow to make sure that the pump is rotating in the correct direction. You'd be amazed how many times that people install pumps and they hook the leads up backwards. And that's the thing with some of these pumps, you can hook things up backwards and the pump will actually turn the other way. And so make sure that your pump is, you know, I always put a little arrow on there. So when it starts up, I make sure it's spinning the correct way, especially after a pump change or you're putting another pump in. Always check direction. Look at the type of seal you have. If it's a water seal, make sure you have the water flow on and that it's flowing, and that protects the shaft from any sort of wear, and prime the pump. Because you can have a centrifugal pump like we talked about, it could be running for a long time. It's not going to do anything unless there's water flowing through it. So there has to be water in the pump bowl. In order to do that, I like sometimes you can completely fill the pump and suction lines with water. And some pumps I find that there's a valve at the top in the casing, and you can actually put water into it and it will fill the pump all the way back to the source. And then you can turn the pump on and it will pump. And again, on any sort of these positive suction pumps, there's sometimes an air release valve at the top, and making sure that that's open so it can vent water from or air from the top. So, and again, it says here, never start a positive displacement pump against a closed discharge valve. That's not a good thing. We talked about a water hammer, and I've seen this, I've seen some serious water hammer in my time. Again, if water has lots of energy, right? And if we're starting a pump, and that's why we go back to the soft start and the variable frequency starting drives that make the pump start very slow, and it's so that it doesn't start water hammer. Imagine a 400 horsepower pump and I turned it on full speed right away. I will blow the pipes out of the ground. So you have to make sure that when water is moving, or you're going to get water moving through a pipe network, that it's done as slow as possible, because it can cause issues. You can start a pump too quickly or valve operation too quickly. And I find this in fire hydrants a lot. Sometimes the fire department will open a hydrant too quickly or close it too quickly, and it will actually cause a hammer, and it'll break the pipes. I had a fire department crew that every single time they would open up the fire hydrant, they would actually break the plastic pipe, because they just were, you know, they must have had a fire department member that was very quick to close the hydrant, and almost too quick. And you have to do it very slow. So you guys out there turning pumps on and off, be very, very careful. That's why I like in centrifugal pumps, I'll turn the pump on and then I'll slowly open the discharge valve. I'll open maybe a crack and then a quarter and a half, 3/4 open, and I give it time to pressurize. And so you're not get that big hammer in there. It can cause a lot of issues. Again, water hammer to prevent it, slow start and stops of pumps, open valves closed. Another thing that happens is air chambers or air release valves aren't serviced properly, and you get a thing of air in there, and that can cause also water hammer as well. So making sure that your air release valves or your air chambers are functioning correctly. And again, I've seen it time and time again, water mains completely destroyed because of the big hammer effect of turning things on and off way too quickly. So be very, very aware of that. It does cause a lot of problems. Another big problem in water systems, especially in the pumps, is something called cavitation. And again, this is when the absolute pressure of the pump drops below the vapor pressure of the liquid. And again, you get these little bubbles.
Good morning. Good morning.
Ignatius, I can still hear you, Ignatius. Thank you. And again, it comes from poor design, and I've seen this a number of times. And the way you can hear it and say if that's happening, you'll actually hear it. It sounds like a gravel. It's like, and that's what it sounds like. Or it'll go ping, ping, ping. If this is left like this, and what it's actually doing, every time you hear that ping sound, it's actually putting pits in your impeller, and it can actually eat the impeller to nothing. And it does a lot of damage. Take a garden hose next time and bend it a little bit. And you hear that sound, right? That gravelly type sound. And that's exactly what it is. You're creating a low pressure, and so much so that it's causing, you can hear that it's almost boiling the water inside that pipe. And that's what happens. So when you ever have a garden hose next and you kind of kink it, you can hear that sound. That's cavitation. And that actually can do a lot of damage to your pumps. And again, it comes if your suction lifted too high, if there's too much vacuum, right? By doing this, you're causing a venturi, and it's causing almost too much vacuum, and it's causing the water to go into a state of cavitation. Pump maintenance too. Again, like anything, and like my electrical and my mechanical, checks and stuff, schedule and proper lubrication of the bearings and other pump components are really important. Look, tear downs of the pump if things are starting to go sideways. And again, you're going to look at those things, hearing, you're going to look at heat, you're going to, look at time too, right? And amperage, all these things you're going to look at in your pumps and determine if they need to be rebuilt. And even, if you're looking at your pump, it's been in place for a long time. You have to make sure that, you're repairing the wear parts. And those are something called wear rings and bearings. And those are things that are going to wear and protect the main components, which is going to be the shafts and the impellers and stuff. Using proper startup procedure and priming, if that's required. And again, as an operator, making sure that anything that's weird, temperature, noises, leaks, anything that you write it down, monitor it to see if it gets worse, because it could cause problems. You're also going to look at, back to that water seal, you're going to look at your packing to see if that's okay. And that packing has to be replaced every once in a while. Your water seal pressure should be about 5 PSI, greater than the maximum pump suction pressure. And again, that's so that you're creating that positive pressure, right? And they should leak. Whenever you have new operators and you have a packing and it's leaking and it's supposed to leak, make sure it's either labeled that way or tell your new operators not to ever fix it, because you need that leakage. For grease sealed packing glands, again, make sure that there's enough grease available. Sometimes you've got those automatic greasers and you're always keeping an eye on that. Alignment of pump and motor is also really key, right? So if it comes out of an alignment with the coupling, and I think I got a couple of pictures of the couplings coming up here, but making sure that nothing gets out of line or it's lined up properly. And I've actually seen this as an ABC test question, is drain the pumps if they're not in use for long periods. Because if you got water sitting in a bowl and it's not used for a while, that could actually rust or cause corrosion on the inside of that pump. And so you don't want that. So if you're going to be a couple of months before you use this pump again, drain. A lot of them have a drain port at the bottom, drain the excess water off so you're not doing damage to your impeller and your pump bowl. So let's talk about how we size a pump now. And when we look at our pump supplier, they're gonna ask a number of different questions to you, and they're gonna provide you with a pump curve. And in these pump curves is a graph showing all these things. How much, they'll say that this particular pump can put out this much flow, and flow is always represented by the letter Q. So in the industry, flow is always Q. They're going to look at total head, how much pressure, that's what that means. And that's going to be in the form of H, how much power is required and how much energy or efficiency. So what we want is the best of all these. We want to have the amount of flow we need with the amount of lift and head that give us the best efficiency. So we're going to look at these pump curves to make sure that these are going to work for us. First one I'm going to look at here is going to be the HQ curve. It shows the relationship between the pressure and the capacity or flow. And that's probably your two biggest things. How much of this pump going to lift and flow? And those are your two biggest things. This curve will indicate what flow this pump will produce at a given lift, right? It's generally the capacity of the pump will decrease as the lift increases, right? And you want the best part. The design point and the capacity at where the head at the pump is shown on the HQ curve, and we'll look at these curves in a second. What you're going to look at is basically what's more important, lift or flow in the business or the intended operation of this pump. And so you want to have the best of both worlds as well as getting the best efficiency. When we look at the EQ curve, this looks more at efficiency during the flow. In sizing a pump system, the designer selects a pump that will produce a desired flow with the desired lift at the best efficiency you can possibly get. When we look at the P and the Q curve, it's the power. It indicates what power the pump requires for a given flow. Let's take a look at one of these curves here. There we go. So here's a typical curve here, and it's, sometimes there's other ones. This particular one here shows that if I want to produce 20 US gallons, where's my pen here? Green. So if I want to produce 20 US gallons, I got to go up to my curve, and it's going to be right here. At 20 US gallons, I'm only going to get 15 feet of lift. So if I need say 25 lift, this isn't going to do it. It looks like the maximum lift in this particular pump here is going to be 22. So at 20, if I had to do the maximum lift of this pump, I can only put out maybe 7. So that's really not a whole lot. And maybe that's not enough flow for what I need. So maybe this is the wrong pump. So you always have to make sure that you're providing the best pump for the process that you have. Sometimes I'll have an efficiency curve, right? And that efficiency curve, they'll have another one that a line that comes in like this, and it'll have the efficiency. So basically the point where all these meet the perfect part, is usually right in the middle, where the best efficiency, the best lift, and the best flow. And that's all right about here. So this particular pump, I would say, can produce safely 19 or 20 US gallons per minute at probably at about 15 feet of lift. And this pump, that's what it's perfect. You don't ever want to have a pump that's you're at the either end of the pump curve. You want to be right in the middle of that. And it gives you the best course of action for moving forward in a pump. So take a look at the pumps that you have in your systems and see if you can see the pump curves and see if, where you guys are with the pump curves. It's really interesting to see these things. We talked a lot about pumps. Let's talk about the motors, right? Motors and pumps are usually together, but they're treated very separately. Motors convert, again, electrical energy into mechanical energy. So we're taking that electrical energy moving it towards driving equipment such as pumps and blowers and whatever we need to do our business out there. When motors are connected to electrical energy, they develop a twisting effort, and they call that torque. That's the twisting that rotates the shaft of the motor and provides the power needed to drive the impellers of our pumps. Parts of the motor, again, these are your typical parts. You're going to have a frame, and that's the housing that the pump is going to sit on. You're going to have a stator, and the stator is the non-moving part of the motor, and it's usually like a round, and it's got coils on the inside. So if you take it, it looks like a hollow pipe, really, but it's got coils on the inside. And the coils are usually of copper or aluminum. Copper is preferred because as aluminum gets older, it tends to flake and has some issues. So I do recommend sticking with copper if you can. Inside though, the rotor fits inside the stator, and the rotor is the rotating component of your pump or your motor. It's the rotating part. And again, to make that thing nice and square inside there, it's going to be supported on bearings, and they're going to hold the rotor or the shaft in position. And again, provide that mechanism so it rolls easy. This does show up on the ABC test a lot of the times, parts of a motor. So really review that, making sure that you understand what each of these units are. Stator and rotor being the most two important things that you're going to see here. Another really common question I see come up all the time is, what is the most common type of motors used in a water treatment or industrial process? And it's usually something called three-phase AC induction motor or three-phase alternating current. Another thing that's asked, if one of these phases doesn't work, if one phase is interrupted, the other will continue to run, but it causes more heat. That's a question. Can a pump still run if you lose a phase? It's hard to start. They will go, but it's hard to start. And if they are running, the others will continue to run, but it's harder on that motor. It creates more heat, and the motor's not going to run as efficient, and you're going to see more amperage and more issues. So keep that in mind. It will run, just not well. Two main types of three-phase motors, and one's called a squirrel cage induction motor, and one's called a wound rotor induction motor. The squirrel cage is probably the most widely used one. It's the one you're going to see a lot in the centrifugal pumps that you guys will be using, fans, blowers, and sometimes on your generator sets. The second one is more, it's got high-speed torque. It's used to have more heavy-duty on-off applications, and I mean, like cranes and hoists and that kind of thing. And I don't see them as much in the water treatment industry. The squirrel cage one, absolutely, I see that one all the time. So I tend to see those a fair bit. We talked about electrical drives. Let's talk a little bit about the mechanical drives. And some of the drives here, and again, you have, if your pump is over here and your motor or is over here, you need something to drive it, right? Typically, you'll have couplers, and we'll talk about those in a sec, but if they're offset or the motor and the pump are separate, you'll have to have some sort of drive. And there's two main ones are used, are belt drive, which are pulleys. One's on the pump shaft on the output of the pump, and one's on the output of the motor, and it will turn the desired equipment. They can use a rubber type belt material, or you can use a chain drive. You know, again, a bicycle is probably the most common example of a chain drive, right? We've all seen those. Whereas, say, in this particular example here, that's a typical belt design for moving. Again, making sure too, from a safety perspective, that this is protected, so you don't get your hands caught in there if these things are moving. You know, and making sure that the belts are serviced all the time, because those belts can break and cause a breakdown. More typically, though, what we see is those direct coupled connections, right? And where the shaft ends of the pump and the motor are lined up together. And we talked about the importance of having that pump lined up properly. And a lot of times you can use a mechanical level or a laser level device to make sure of that. In between it, though, you're going to have something called a coupling. And these are pretty typical couplings. They're a rubber usually, and they have a metal on either end, and it takes a little bit of flex, right? So that it's not hard couple. It will take a shock load of a start up, and so that you're not damaging pumps. It gives much smoother power generation from motor to pump. And this is typically what I see that's used a fair bit. Again, when you take your pump apart, make sure that these are serviced or looked at to make sure that nothing's damaged here. But this is typical direct coupling. So next time you're tailoring rounds of your plants and your systems, take a look at the pumps you have and see how are these things coupled together. Typically, you're going to see this. This is going to be what you're going to see the most. Again, flexible shafts are used too. You can see like a drive shaft, for example, that sometimes is used less. I don't see it as much in the water treatment industry, but you have a pump and a motor, and there's a shaft in between. You can also have right angle drives where it's got a universal joint and it's turning something that's to the side of it. So there's all different types of drivers, mechanical drivers, that is. Shear pins. And I mean, we see these all over the place. and they're protective devices, really. They're like breakers, right? They're designed to break before a real issue. And that could be an issue with the shaft or gears, that something's wrong, or something, a bearing or something has seized up. These shear pins are designed to break before damage is caused to the actual unit itself. So these are great things. If you keep breaking shear pins, there's a reason for it, and that should be investigated right away. Also, it's really important to make sure that you put the right type and material of shear pin together, because it shouldn't break unless it really needs to. They're designed to break before damage happens to the actual piece of equipment. I've seen it where, you know, shear pins would always break, and the operator would put in a big bolt or something in there to make sure it doesn't break again. Well, of course, what happens? It damages the shaft or damages the piece of equipment. And now it costs a lot of money where it probably could have been fixed properly the first time by actually troubleshooting this properly. And that's a shear pin. So always be aware where your shear pins and always have a good supply of proper shear pins. Don't use nails, don't use screws, don't use bolts, use a shear pin, a proper one. We'll talk a little bit about flow measurement. And, you know, flow measurement is pretty important. We talked a little bit about leak detection last week, and you want to make sure that you produce all this water, and you want to make sure that you're saving this water or knowing it's getting to your customer. So water production, you want to know, how much water did I produce? Plus two, if you're charging your customer for water, you want to know how much they used. You want to know how much you're losing in your system. Typical systems will lose 15% of water. And so that gives you an idea. If you're losing more, then, you know, it tells you that there could be some issues up there. Operational control, right? You want to make sure, and for dosing purposes, right? You need to know how much water is coming in so you can put the right amount of chemical in that water. So you need to figure out what you need to do. So water meters are used, and again, they're used to calculate the flow component of your system. There's a bunch of different styles here: propeller meters, nutating disc, mag meter, and differential pressure meters. And these are really interesting. My drawing guy up here. So propeller meter, again, large industrial meters are usually propeller meter. I've seen them a lot of times. So, you know, it will measure flow, and they're not overly accurate. You know, they'll do the job, but they're not overly accurate. Nutating disc is your domestic in-house water meter. And that's usually domestic customers or your customers. And they're usually the 5/8, 3/4 inch meters that are in people's houses. Very, very typical. And they have a disc that does this. It's a nutating disc meter. Your plants and your stations usually use a mag meter, and it's a magnetic meter, and it's actually counting the ions as they're flipping by on sensor. There is no moving parts on the inside. So to me, when there's no moving parts, that's ideal. Anytime you have new moving parts, you have chances for wear. And when you have less moving parts, you have less wear, which means these are more ideal. If there's no losses, no wear, which is perfect. The mag meters use, now the thing with the mag meters is that they weren't used for more domestic or smaller purposes because they weren't made or they're very expensive. So the larger meters were used. Now they're becoming smaller and more robust, and they're a great meter to use. The differential pressure is really interesting. So if I had a tank of water here, and I can actually have a level transmitter sitting at the bottom of the tank. And let's get my blue water here. So I have my blue water in the tank. And the pressure of that water is pushing down on the transmitter. Right? And sometimes it could be used to correlate a flow. I use these for flow. If I had a weir and water was spilling out of here, I can actually take a reading here and with an engineered calculation, know how much flow I have. I do this for lakes and river flow. I have an engineered surface like a waterfall. I'll measure across it. And I know that the distance of water going over the engineered surface of the waterfall, you know, every millimeter of that will change the amount of water coming over an engineered surface. And I use these all the time. Level is equal to pressure. And then I also, level can also be correlated over an engineered surface to calculate flow. You usually see this as called a V-notch weir. And that's where you'll see it, a V-notch weir, where this is an engineered surface. Water will come through a V-notch weir, and this is a calculated surface. So the distance in water between the surface and the engineered surface can be calculated. And it's a big, long formula, but it does work. Especially for flows like for, you know, because you can't put a mag meter or any of these meters in a stream flow. So the differential pressure meter, or they also call it a delta P meter, is used in these cases. And again, here's a chart on rotameter for smaller stuff. I mean, when you talk about your chemical systems and stuff, a rotameter is usually used, right? And again, that's that tapered glass look. What it is when the fluid is flowing, a float will rise until the weight is balanced by the upward thrust of the fluid. And again, there's usually a scale, and I got a picture of one right here. It's important here to make sure that you're reading in the right location on that. So make sure you read on your manufacturer specifications of don't read down below, usually read on the top of the ball. And sometimes there's a ball or a plug or something that represents on a scale here. And this is a typical rotameter, is what it's called. Let's talk a little bit about chemical feed systems. Again, you can feed manual, right? So basically you're going to take a test, and let's use chlorine, for example, water flowing, and you see the water flow is increasing. You're going to, as an operator, turn up the flow of the chlorine pump so that you're getting the proper parts per million of chlorine to water mixture. The second one's called the flow paste, and it will automatically, and this is where we go back to PLC, right? So that you have water flow flowing, it's sending a signal to the PLC that if my flow increases, can you increase the pump for the chlorine? And so you're always keeping consistent ppm, or parts per million. That works really well. You can also have compound loop systems, and this takes it to one whole more degree. It'll say, okay, as the flow increases, increase the pump. And now it's actually going to look now at a third variable. It might look at something called the chlorine residual. And if you have a chlorine residual meter, it'll say, okay, well, I'm doing everything, but I'm not quite getting the required chlorine residual. So it will actually say, okay, maybe you have to increase this pump speed a little more because it's not enough. So it will actually look at another or a third variable to make sure that it's working. So it's not just looking at the flow, it's now looking at the flow and the desired result at the end. And it gives you a feedback to see, okay, am I doing okay, or do I need to adjust it? And this is a compound loop or feedback control system. It usually takes into account a third variable. Some of the feed systems, and we talked about that, as our diaphragm pumps, right? We talked about the peristaltic pumps. We looked at that last day. In a gas chlorine system, you're going to have gas feeders or dispensers. And we talked about that during the chlorine portion. Vacuum injectors, you can have dry feeders where you have to have dry product mixed with water, or called slaking, and that will provide some sort of chemical feed for you. We talked about diaphragm pumps, and again, those were probably the most commonly used type of pumps. I'm seeing more and more peristaltic type pumps being used now in the industry, but at one time, diaphragm pumps were king, and that was what was used everywhere. Now people are moving more towards the peristaltic style pumps. And again, typical feed system. Like all things, they need maintenance and calibration, and making sure that we, again, because these they're using chemicals, they are going to wear over time, and they need to be calibrated all the time to make sure that they're giving you the correct amount of product that's needed, especially on the chlorine pumps, right? You want to make sure that, something that important, that they're serviced all the time. Leaks and stuff, especially with chlorine, liquid chlorine, it crystallizes a lot on the fittings, and making sure that we're cleaning those and servicing these pumps to make sure. Again, tested in calibration, I can't stress that enough, especially if you're using it for any sort of chemical addition. A lot of the times, the smaller pump skids, they have a calibration tube or some sort of drawdown tube, so that you can take a stopwatch and actually measure and make sure that that pump is putting out exactly what you think it is. And that should be done on a regular basis to make sure that things are calibrated and things are properly maintained in order to provide that continuity. All right, and that brings us to the end of week number 10. And thank you very much for that. We have one more big lesson next week with the lab stuff and safety. And then we're gonna get into a big review on the week 12. And you guys should be ready to pass a ABC exam, I hope.
Yeah, great stuff. We get into the end of this, so that's great. And I hope everybody began their revision sessions. So I think we're going to have a final revision session that is in week 12, is it, Mike?
Yeah, week 12. what I plan to do there is I have a 50 question exam that we'll do together. I'll put a question up on the PowerPoint, and then we will use the chat function to work through the question all together. And I will explain if there seem to be difficulties with that question. We will talk through it. So that's the whole idea of week 12. Is I've used questions that I've presented to you guys throughout the 12 lessons or the 11 lessons, and we will be working through those 50 questions, which some of them are going to be pretty tough. And if there's some explanation from those questions, that's going to be the bulk of week 12.
Okay. All right. Thank you very much, Mike, and have a wonderful day.
Yes, you guys too. Thank you.
Yeah, and same to all the operators, and see you at 3 with Mike Ipen for water distribution, those of you following water distribution. And just to remind you that we will not be hosting a webinar today. We will resume on the April 7th with the webinar series. Okay, have a wonderful day. Bye-bye. Ignatius Jean signing off from CAWASA.